Hello children, welcome to the physics lesson. We are in unit 6 electrostatic force fields. In the previous session we discussed the competency level 6.1. Today we are going to discuss the competency level 6.2, which is quantifies the electrostatic field using the flux model. Now you have to understand that competency level 6.2 is a continuation of level 6.1. So, it is important to revise what we have learned in the previous session. Now, we first spoke of what electrons, what charges are. We said the charges are positive charges and negative charges, that it is a property of matter that will allow it to experience a force when kept in an electromagnetic field. We also learned that when two charges are kept apart, that they are going to experience a mutual attractive or a repulsive force. By the Coulomb's law, it explains the mutual attractive or repulsive force exerted between two point charges. The law states that the magnitude of the force is directly proportional to the product of the magnitudes of the two charges and is inversely proportional to the square of the separation between them, and the epsilon, a property of the medium introduced as the absolute permittivity, and we spoke of vacuum permittivity and relative permittivity of the medium. Now, we said when two charges are kept apart in a space, that each charge produces an electric field around it. So, one charge is always kept in the field produced by the other charge. So, we use this idea to express that the charge not only produces an electric field, but also can be used as a source to detect the presence of an electric field. So, using that idea, we define electric field intensity. We said the electric field intensity can be described as the electric force exerted on a unit positive test charge. So, the source charge creates an electric field, the test charge detects it, and the direction of the electric field, we said, is given by the direction of the force exerted on the positive charge. We extended this saying that if the field intensity is the force exerted per unit charge, then if we kept a charge q in the place, the force exerted by the charge q would be given by the equation F equals Eq. Then as a next point, we used Coulomb's law to talk about the field intensity produced by a point charge, how the field intensity vary with the distance around a point charge. So, by the Coulomb's law, we came to the expression E equals 1 upon 4 pi epsilon q over r square. So, the source charge q produces an electric field with the distance r, the field intensity is given by the equation expressed here. Lastly, we spoke of the concept of field lines. We said we use field lines to visualize the electric field, and we said that the field line represents the path of a positive charge, and we constructed field lines using a few rules. The first rule we learned was that always the field lines begin from a positive charge, end from a negative charge, and when you take a plus and a minus charge together, field lines are drawn from the positive to negative. And also we said the field lines are drawn proportional to the charge. So, this shows that both charges are equal but unlike. So, the same number of field lines are drawn around it. So, if the charge differs, they are opposite charges and they are also unequal charges. This is negative charge is stronger than the positive charge. So, we have drawn more number of lines around it, fewer number of lines, but it is explained by the concept, the rules that we have we gave to express the concept of force fields. And then in the presence of two like charges, we explain the null point here, saying the absence of electric field there, and always the field lines repel from each other. That is an example for the field lines, construction of field lines between two like charges. Then it was also important to know how the field lines appear between two conducting plates. In this example, we discussed earlier positively charged plate, negatively charged plate. In between, we have kept a conducting sphere uncharged. So, in the presence of the positive charges, a negative got induced. In the presence of the negative charges, a positive got induced. So, the lines were drawn from positive to negative, from positive to negative, and the other point is that always the field lines must be perpendicular to the conducting surface. Then if we come to the flux model of electric fields, there are a couple of points. We used field lines to visualize the electric field, but then the field lines helped us to visualize it, but then it was only a qualitative description of the field, electric field. We were not able to determine anything, but then we said if charge increases, we have to draw more number of field lines. Then if the charge concentration, the field concentration to show the field increases, we said the field line concentration increases, the electric field intensity increases. So, likewise it was always a qualitative description using the field lines. Now, the flux model helps us to get a quantitative measurement of the electric field. We say the flux model is a concept that discusses the flow of electric field, and then that it will give us, it will help us to determine the electric field intensity quantitatively. We learned the Coulomb's law, where the Coulomb's law explained the electric field intensity in a field produced by a point charge. So, we can't use the same law when in order to determine the field intensity produced by a distributed charge. For example, practically we do not find any point charges in practice. What we always find would be charges distributed on bodies, because when a body is charged, charges get distributed over the body. So, therefore, really practically we can't actually use Coulomb's law to determine field intensity. So, we use the flux model here to determine field intensity by the produced distributed charges. When we come to the electric flux, the model, we say the electric flux is described as the rate of flow of electric field through a given area. So, there are two words associating here, the word electric field through a given area. So, two words. So, this shows that the flux depends on the electric field's properties as well as the area we choose. Electric flux is said to be proportional to the number of electric field lines. Now, electric field lines are drawn to help us visualize the electric field, and the flux is a more quantitative measurement. So, the flux must be, when we consider the flux model, we have to consider that electric flux is also proportional to the number of field lines we draw, and we know that the number of field lines will be proportional to the charge, the source charge that produces it. Now, we consider all that together when it comes to the flux model. So, when we think of the electric field lines, that represents the flux model. Flux is directly proportional to the field lines, and when we consider the field lines passing through a certain surface, there will be three factors affecting. So, if I repeat, we say that electric flux is a more quantitative measurement of the electric field, but the electric flux depends on the field intensity, or rather the electric field as well as the area that we choose. And then electric field is represented by electric field lines, and the electric field lines are proportional to the charge. They say that the electric flux is also treated to be proportional to the electric field lines. So, when we take it all together, let us see what properties will, on what properties will the electric field lines in a surface will depend. The first property is the strength of the electric field, which is represented or denoted by the density of field lines. Now, if I take an example, you see I have chosen two areas, two circular areas, both areas are equal. I have taken same size areas, but in this the line spacing is greater, whereas the second one line spacing is less. So, this shows by the electric field line concept, what we learned there, the line density represents the strength of the electric field. So, if the line density is less, it shows that it is a weaker electric field. When the line density is more, it shows that it is a stronger electric field. So, this shows that E1 is smaller, weaker than E2, intensity E1 is less than E2, and so we see there are more number of flux lines, field, flux is proportional to field. So, stronger flux, a weaker flux, more number of field lines, lesser number of field lines, two equal areas. If you think of the second point, it depends on the area of the surface that we choose. So, for example, same line density, you see the line spacing is the same. So, it is the same line density, which means the strength of the electric field, field intensity are equal. But I have chosen a smaller area or a bigger area. So, what happened? This smaller area occupies fewer number of field lines. This larger area occupies more number of field lines, indicates that higher flux through the area, lesser flux through the area, described by that. Then if we think of the third point, is the orientation of the surface with respect to the lines of forces. For example, I have chosen equal identical fields. You see the line density is the same, which means field intensities are equal. And I have also chosen equal areas, same area, but one area space, one surface is kept perpendicular to the field while the other has inclined to it, shows that fewer number of lines pass through that area now, same area, but occupies a different number of lines, but through the same area it occupies more lines, which shows higher flux density, higher field density. So, higher flux linked with the area, lesser flux is linked with an area when the orientation changes. This can be further explained by the diagram there. So, the same area when kept at right angle to the field, more number of field lines pass through that, and as the orientation changes, the number of lines passing through the same area become lesser and even lesser. So, what we learned here was that the flux quantitatively will be represented by field lines, number of lines qualitatively. So, the number of field lines that occupies a space vary based on 3 points. One was the strength of the field, 2 was the area we choose, 3 was the orientation. We also saw that the maximum number of field lines will be occupied when the surface area we chose is kept perpendicular to the field lines. Now, when we come to the flux model, to use the flux model, E flux or electrostatic flux or flux of electric field intensity denoted by the symbol phi E, if you consider a uniform electric field, the reason to choose a uniform electric field is because in a uniform electric field, field intensity will be uniform throughout. So, all over the space, in the 3D space, electric field will be uniform. So, it is easier for description. So, if I consider a uniform electric field, now we give a quantitative measurement to this concept of flux. You have to understand this is a concept. So, we are giving it a definition. We say that electric flux can be taken as the product between the electric field intensity at that point and the area we chose. That is what we explained in the previous parts. So, higher field or higher area gives rise to a higher flux is the idea. So, we have to consider a perpendicular area, the area must be perpendicular to the field and the field intensity E at that point, the product of the two will give us a quantitative measurement to the electric flux. So, unit of E, if we take unit of E, E's SI unit would be newtons per coulomb and the unit of A is meter squared. So, E times A gives us the SI unit Newton meter squared per coulomb. Now, if we try to explain this a little bit more. So, in a uniform electric field of field intensity E, if the area I have chosen is perpendicular to the electric field, the total electric flux passing through the surface or linked with the surface is E times A. But if we choose an area inclined to the electric field, you see the total number of flux or the field lines linked with it is shown by the arrows. So, I have to calculate the flux. In order to do that, I have to take E times A. So, it is a uniform electric field, field intensity is E, and the A must be the perpendicular A that cuts through the same number of lines. So, in that case, I have to resolve that surface to the perpendicular direction. So, the area perpendicular to the electric field will be A cos theta. So, field would be E and area would be A cos theta. So, let us move on a little bit to explain this furthermore. So, if I take an example, theta is the angle between the electric field vector and the surface vector. Surface vector, the surface we have chosen, the vector can be taken as direction perpendicular to that. So, the surface is this, vector would be that. So, theta would be the angle between the electric field vector and the surface vector. So, if I take an example, when theta is 0, you see that is the direction of the electric field and the plane, the surface is kept perpendicular to it, meaning the surface vector is in the direction of the electric field. So, the electric field's direction and the surface vector's direction are the same. Basically, surface is kept right angle to the electric field. In that case, we know the maximum number of flux lines linked through that. So, the total flux can be taken as E into A. If I take another example where theta is 90. So, that was the first example, electric field and the area. Area is perpendicular to the electric field, but now the two vectors were earlier in the same direction. Now, the two vectors are right angle. For example, I am going to take it like that. So, the electric field is that way. I am taking the A vector in the direction perpendicular to it, that is the plate. Now, even when you look at it, you can see that really there are no flux lines, field lines passing through the area. Area is kept parallel to the electric field. In that case, if I substitute to the equation, the area that is perpendicular to the field is 0. So, the flux that is linked with this area would be 0. Take a different angle when theta, angle between the electric field and the surface is inclined. So, the vector is towards that direction. So, the direction of the surface vector and the field would be theta, and you have to resolve and take the perpendicular component. And so, when you take the perpendicular component, E into the area perpendicular to it would be A cos theta. So, that describes the quantitative measurement of electric flux. Now, we learned that electric flux can be expressed quantitatively as the product between electric field intensity at a particular point and the flux the area perpendicular to the field through which the flux is linked. We also said that electric flux is proportional to the field lines that we draw. But then we have learnt earlier in the field concept that field lines, when we draw field lines, the field lines must be drawn proportional to the charge that produces the field. So, if you try to link those two together, that is given by the Gauss's theorem. First we learned about the flux model. The Gauss's theorem states the relationship between the flux and the charge, source charge that produces the flux. The theorem is the total electric flux linked with a closed surface is 1 upon epsilon times the charge enclosed by the surface, where epsilon is the electric permittivity of the medium in which charges are immersed. Now, according to this, let us see whether what we learned is the same. So, flux is proportional to the field lines. We learned in the field concept, field lines are proportional to the charge. In other words, we see that by the Gauss's theorem, the flux is proportional to the charge, but then it is equivalent to 1 upon epsilon times. So, we introduce the flux by means of the charge, the source charge that creates the field and hence the flux, and then we again gave by the flux model the quantity of flux, the amount of flux is given by that. So, if you join the two results together, we come to EA Q over equals to Q over epsilon. If you try to explain this, this shows that by the charge Q in the field, electric field of intensity E at a particular point, the net flux linked within area, the perpendicular area, the relationship between the factors are expressed by that. So, that is the source charge that creates the electric field, that is the field intensity at the chosen point, and that would be the surface through which the flux lines are linked with. When we try to derive, I said when the purpose of introducing the flux model, the Gauss's theorem and the flux model itself is to derive relationships, mathematical expressions, relationships for distributed charges. For point charges, by the Coulomb's law, we have already derived a relationship. So, when deriving expressions for field intensities using the Gauss's theorem and the flux model, we have learned two. Using the Gauss's theorem and the flux model, there are two steps that we have to do. The first step is we have to draw a Gaussian surface. We were talking about surfaces drawn. The word Gaussian surface comes by the idea of surface that we draw, use the Gauss's theorem. So, we say there are 3 points that we have to consider when drawing Gaussian surfaces. We say a Gaussian surface is a closed surface in the 3-dimensional space through which the flux of the vector field is calculated. The vector field in this lesson is the electrostatic force field. So, we have to, when we draw the Gaussian surface, we have to draw it as a closed surface. We know it is in the 3-dimensional space, and we have to draw it as a closed surface inside the vector field, inside the electric field. The second point to consider is that the Gaussian surface, it is an arbitrary closed surface used in conjunction with Gauss's law in order to calculate the total amount of source quantity enclosed. Now, in our example, in our lesson, the source quantity now is the charge. So, whether it is a point charge or a distributed charge, it is a charge that produces the field. So, the source quantity here would be the electric charge. So, we learned 2 points. The first point says that the Gaussian surface is a closed surface that you have to draw inside the electric field. The second point says that this closed surface, the Gaussian surface, when you draw, must be drawn enclosing the electric charge. Then the third point says that the Gaussian surfaces must be carefully chosen to exploit symmetries of the situation, and that the magnitude of the field along the surface, Gaussian surface, must be a constant. So, once you draw the Gaussian surface, if you move along the surface, the electric field intensity's magnitude at any point must be the same. So, if you put it together, the Gaussian surface you have to carefully draw in the 3D space that the field is exerted, and you have to draw the Gaussian surface enclosing the charge that produces the electric field, and along the surface that we have drawn at any point the field intensity's magnitude must be the same. Now, that is the first thing we have to draw in deriving expressions. We have to choose a Gaussian surface appropriately. The second point is that we derived a result using flux model, using Gauss's theorem, and using this result and the Gaussian surface, we can construct, derive expressions for any kind of electric field. So, let us begin by what we are familiar with. This we derived using Coulomb's law. For a point charge, we already have an expression. Let us see whether we come to the same expression. Near a point charge, if the point charge is a positive charge, the field lines represent by the arrows, and it is an isolated point charge. So, you have to draw the field lines symmetrically. We have learned this, and now we have to choose a Gaussian surface that fulfill the above three conditions. It must be an enclosed surface, it must be drawn in the field, and it has to have the same field intensity at any point along the surface. So, if I choose a point at a distance r from it, that is a positive charge that constructs the electric field. At a distance r from it, let us say the field intensity at that point is Ex. Well, according to the symmetricity, we know at the same distance at any point. So, from the point charge at any distance in the 3D space, the field intensity must be the same, symmetric. It is a symmetric, the field model, the field concept is a symmetric concept. So, therefore, at any point at the same distance, field intensity must be the same. So, now I have to choose a Gaussian surface inside the electric field enclosing the charge. So, I have chosen a spherical Gaussian surface. See if it is understood. The point charge, you draw a spherical Gaussian surface centering the point charge. So, along the surface at any point, intensity, magnitude of it is the same. And you see these lines are perpendicular to the surface also. So, let me mark that also. So, now I have chosen my Gaussian surface. So, I have to determine field intensity at point x. So, drawn the Gaussian surface, going to substitute to the equation Ea equals q over epsilon. So, at any point on the surface, field intensity is Ex, and the charge delivers flux in the 3D space. We have drawn a spherical Gaussian surface. So, we have to substitute to the area the net surface area. So, when I substitute on a sphere, the net surface area would be 4 pi r squared, and the Gaussian surface encloses the charge, source charge that produces the field. So, therefore, q would be the net charge enclosed that exists inside the Gaussian surface, epsilon permittivity of medium. And when you solve it, we see that the field intensity comes to 1 over 4 pi r squared q over epsilon. Now, that is a result we are familiar, that justifies that what we have derived from the Coulomb's law is valid. And if we try to show the representation graphically, electric field is a vector property, and that the field vary with the distance in a relationship inversely proportional to the square of the distance, and it is a vector, and that is the graph we get that we have drawn earlier also. If we try to explain the variation of field intensity with the distance, field intensity is a vector. So, we have to indicate the plus minus of the graph, and then that also by the equation it is clear that field intensity is inversely proportional to r squared. In that case, we say the graph is drawn like that, the vector, and with the distance field intensity decreases rapidly, graphical representation. If we come to the next example, charge conducting sphere. Now, let us explain this a little bit before we come to the application. If you take a conducting sphere, it is a neutral sphere. The word conducting refers that there are free charges, free electrons, free carriers are there. So, the charges are able to flow along the conducting channel. It allows a good conducting channel for the charges to flow. When you take a neutral conductor, and if you give that conductor a charge by any of the methods that we have discussed before, the moment you give the body, the conductor a charge, what happened? The charges experience a Coulomb repulsive force, and as a result the charges start repelling from each other, and it is a conducting sphere. So, the charges start to conduct all over the space, repelling from each other, and will settle at a particular equilibrium state under the repulsion of Coulomb repulsive forces. So, as a result they will repel and always store on the surface of the conductor, experiencing equal opposite forces. So, whatever the shape of a conductor, when you give a conducting material a charge, the charges will always store on the surface of the conductor. So, now it is a charge conducting sphere. So, when we give the body a charge, the charges will reside always on the surface of the sphere, and we are first going to discuss about the field intensity away from a charge conducting sphere, that is outside a charge conducting sphere. So, if we take an example, let that be my charge conducting sphere. So, in the charge conducting sphere, the charges are stored on the surface of it, and now field lines must be drawn symmetrically. We have learned that the field lines are perpendicular to a conductor. So, the field lines must be drawn right angle to the conducting surface, and the field lines must be drawn symmetrically. It is a uniformly charged conductor, and now that represents the electric field around it. Now, we have to choose a Gaussian surface. So, if I choose a point like x, let us say the field intensity at a distance r from the center is x, for instance. So, by the symmetricity we understand from the center at the same distance in the 3-dimensional space, at the same distance, field intensity must be the same. So, if I draw again centering the charge conductor, if I draw a spherical surface in the 3D space centering the charge conductor, we understand along the surface of the sphere, this is not a circle, it is a sphere. So, along the surface of the sphere, all the points should have the same electric field intensity. So, once again Gaussian surface is a sphere. So, now if I substitute to the equation EA q over epsilon, I want to find the field intensity at any of those points, it is equal. So, the field intensity at point x would be Ex, and the total surface area that encloses the charge. So, the total surface area, once again it is a sphere, so 4 pi r squared, and inside the Gaussian surface the net charge resides, q would be the net charge and the epsilon. And so, if I subject Ex, I come to the equation 1 upon 4 pi epsilon q by r squared. This shows a very important result. That was the same result we got when we had a point charge plus q at a distance r from it. The field intensity we obtained was the same, 1 upon 4 pi epsilon q by r squared, and we get the same result for the distributed charges on the conductor. So, the conclusion we can come to is that in that case we can consider this distributed charge concentrated as a point charge at the center of the same. At the center, if you concentrate this charge and keep it at the center as a point charge, from it at a distance r, the field intensity would be the same. So, whether the charge is distributed or you treat it as a concentrated charge at the center, the result we obtain would be the same. Now, that is for a point outside the conducting charge sphere. If you now think of a point near the charge conducting sphere, so that is the field lines that I have drawn perpendicular to the conducting sphere. This is my conductor. So, to the conducting sphere I have drawn the field lines perpendicular to the surface, that is by the field concept of field lines we learnt it, and the charges distribute uniformly on the surface, and I am choosing a Gaussian surface near the sphere, but outside it. So, for instance, just outside the sphere I am trying to choose, a Gaussian surface. So, once again it is a symmetric system, symmetric flux distribution, field distribution. So, if I choose at the same distance r at any point along the Gaussian surface we have drawn, at any point the field intensity must be the same. So, I have once again chosen centering the charge conducting sphere in the 3D space a spherical Gaussian surface along which field intensity is the same as that. So, my Gaussian surface is once again a sphere. So, if I substitute to the equation E A equals q by epsilon, the field intensity at a point anywhere on the surface is E y, and the total surface area through which the field lines are right angled would be 4 pi r squared, and the charge, all the charge is inside the Gaussian surface, it is just outside the sphere. So, charges are still inside q by epsilon, and so the field intensity is obtained by that, and we see the result is once again the same. So, whether we chose a point at a distance from here or whether it is a point far from the center or close to the center, close to the circle, far from the sphere or close to the sphere, the field intensity we obtain can be taken by treating this distributed charge kept at the center as a point charge at a distance r, field intensity would be 1 upon 4 pi epsilon q by r square. Same result. Now, if you try to go into the sphere, the charges reside on the surface, that is my conducting sphere, all the charges stow on the surface, but I am trying to find a space inside the conductor enclosing the charge. You see, whatever the shape I draw here, I can't enclose the charge because the charges reside outside. I can draw any shape, but it does not enclose the charge. But considering symmetricity, if we once again choose a sphere, spherical Gaussian surface in the 3D space, that is what I get. And that will be my field lines perpendicular to the surface. That is the Gaussian surface that we have drawn inside. Now, if you try to substitute to the equation once again, we see that field intensity at that point z, anywhere on the surface field intensity must be the same, reason it is at the same distance. So, whatever impact must be the same. So, field intensity at point z, the same thing all over, and the surface area would be 4 pi r square, but the Gaussian surface does not enclose any charge, all the charges are outside it. So, the charge enclosed by the Gaussian surface will be 0. In that case, we see that field intensity inside a conducting charge sphere is 0. Now, this is the reason why we did not draw any field lines inside it, all the field lines were drawn outside. That is because inside the Gaussian, inside the conducting sphere or inside any conductor at all the charges reside on the surface. So, the field intensity, the field inside a conducting material will be 0. So, no field, no flux lines, we have not drawn any field lines there. Now, if you try to express this variation of field intensity with the distance graphically, what did we find out from the previous two parts? First point is that inside a conductor, now in this example it was a sphere. So, inside the conducting sphere field intensity is 0. We said inside any conductor, charge conductor, field intensity would be 0. The second point was that outside, whether it is close to the sphere or far from it, if it is a point outside the sphere, the field intensity varied inversely proportional to r squared. We also came to a very important conclusion, said that, so therefore, we can, even though the charges are distributed, we can still treat it as a point charge q at a distance r from it. The field intensity at that point is the same as the result we got there. So, if you put up the graphical representation considering the vector quantity, E is a vector, we see that inside the conductor field intensity is 0. At the surface and outside, the field intensity vary with a rapid drop with the distance, and the vector shows it should be drawn in the plus and minus, positive and negatively it must be considered. If you now come to the next example, near a charge conducting thin wire of infinite length. Again the word conducting, and it is a wire infinite length. You only consider the middle part, infinitely long wire. Charge conducting wire. Now, let us use what we learned, what we already know. We know when a charge is given to a conductor, whether it is a sphere or any shape or wire, all the charges will store on the surface of it. And the charges will store along the wire, and under the Coulomb repulsive force, forces between charges, the charges will store uniformly along the length of the wire at the surface. Now, I am trying to construct a Gaussian surface. So, let us look at the flux lines drawn. So, those are the flux lines, that is one field line drawn right angle to the, it is a conductor. So, if you draw more field lines, I can draw another field line like that. If I draw another field line here, another one right angle likewise. So, the field lines are drawn perpendicular to the conducting wire. Then let us see whether we can picture this. So, that is a straight wire, a conducting wire, and along the conducting wire field lines act like that, perpendicular to it. So, all around the wire field lines act perpendicular to it. And if I try to draw a Gaussian surface enclosing the charge, do you see that to those field lines I have to draw a surface perpendicular to it. So, the Gaussian surface must be chosen as a cylindrical Gaussian surface around the wire. So, the Gaussian surface that we have to choose would be a cylindrical Gaussian surface enclosing the wire, taking the wire as the axis of the cylinder. So, all the field lines will be perpendicular to the Gaussian surface also. If I try to substitute to the equation, you see by the Gaussian surface encloses a certain proportion of the wire, and I am applying the flux model and the Gauss's theorem to that part. So, I need to know the charge distributed or enclosed by the Gaussian surface here. So, for that we introduce a property called linear charge density, because the charges distribute along the length of the wire. So, we use the word linear charge density, which is defined as the charge stored per unit length of the wire. That is, it is a long straight wire, the charge stored per 1 meter of the wire. So, per unit length of the wire, the amount of charge, the total charge divided by the total length gives me the linear charge density. So, lambda would be the number of charges stored in 1 meter length of the wire, coulombs per meter. So, if I now try to use that and substitute to the Gaussian surface, my Gaussian surface is now a cylindrical Gaussian surface of radius r and height L. Height of the cylinder is L. The field lines pass through the spherical body, the circular body of the cylinder. So, now let us substitute to the equation EA equals Q by epsilon. So, at the same distance on the surface of the cylinder, all the points must have the same field intensity, because it is at the same distance, symmetricity. So, let us substitute. The field intensity at the surface is EP, any point on the surface. The total surface area of the cylindrical part, the circular part of the cylinder, let us calculate it. It is going to be 2 pi r into height h, which is 2 pi r into L, is the total surface area, Gaussian surface's area through which the flux lines, field lines pass right angle to. Then the charge enclosed by the Gaussian surface. So, it is the charge that exists in that portion, a length L portion. So, on a unit length charge stored would be lambda. So, on 1 meter length charge stored is lambda. So, on a length L charge stored would be lambda times L. That will be the charge stored within the length L of the wire by epsilon. So, we come to the result EP, field intensity at a particular point at any point on this surface at the same distance, is given by 1 upon 2 pi epsilon lambda over r. Now, lambda for this is a constant, it is the charge stored per unit length, the linear density, linear charge density. Now, according to the result, it is clear that the field intensity vary inversely proportional to the distance. Earlier, field intensity varied in spheres, in point charges, inversely proportional to the square of the distance. Here, the field intensity vary inversely proportional to the distance, and also the field is a vector. that field is the field line is drawn that way, the field line will be drawn to the other direction. So, it is a vector. So, considering those two, E vary with the distance, you see those are field lines, that is my wire, the cross section of it, cross weave of it, that is my wire, and those field lines are drawn right angle to the wire. All these field lines are drawn right angle. We see that the two field lines are diverging from each other, shows that the field line density decreases, shows that strength is decreasing, comes to a result like that. So, if you now come to the graphical representation, direction is opposite on the two sides, and outside the wire field vary inversely proportional to R. Inside it the field will be 0, the field line field intensity will be 0. It is a thin wire. You see the drop in the curve with the distance, field intensity has decreased just like the previous, but here with the distance the decrease in field intensity is less rapid, whereas in the previous it was inversely proportional to R square, it was more rapid. If you come to the next example, near a charge conducting thin infinite plate. Once again, let us understand the meanings of the words. It is a conducting plate. So, when it is a conducting plate, we know the moment you give the body a charge, all the charges will store on the surface. So, on the plate, charges will store on the surface of the plate, and it is a very large plate. We consider one middle part of it, and it is a thin conducting plate. So, now we have given it a charge. So, in the large plate, I have considered a small proportion of it. The charges have distributed on one side. This is exactly the same on the other side, and so on one side the field lines are drawn. I can draw some more field lines like this, draw some more field lines, they are right angle to the surface. So, all these field lines are right angle to the surface. So, now I have to choose a Gaussian surface here. So, that is a cross weave of that. So, the field lines are drawn, all these lines are drawn right angles because it is a conductor. Now, let us choose a Gaussian surface. The surface must be closed and it has to be drawn perpendicular to the field, where such that at all the points the field intensity must be the same. So, if I think of once again a cylinder, but this time earlier the field lines were passing through the cylindrical part, but this time the field lines are passing through the flat surface of the cylinder. So, I have chosen a cylinder of this form, and the field lines passes right angle to the flat surface of the cylinder. Again it is an enclosed surface. So, the area of the cylinder, that area, and that will also be the same area. So, I have to think of the charges stored in this part of it. For the Gaussian surface, to substitute to the equation, I have to find the charges stored in this part. Now, to do that, we introduce the property called surface charge density sigma. Now, in the previous one, along the wire, charges distributed along the length of the wire. Here, the charges distribute over the surface of the plate. So, it is the surface charge density sigma, defined as charge stored per unit surface area. So, sigma would be, if a Q charge stores on A, charge stored per meter squared, a unit area is given by Q over A, coulombs per meter squared would be the unit of that. If we now come to this substitution, when I choose an area along any point of the surface we have chosen, it is at the same distance from the plate. So, anywhere you consider the cross section, the section A, plate area A, at any point field intensity is equivalent to the field intensity at that point EP. And the plate area perpendicular to it, let me take it as A. So, that plate area is A. So, EP times A would be the total flux linked with the. Now, what to substitute to this Q, which is the total charge enclosed by the Gaussian surface. So, this Gaussian surface encloses this amount of charge. We know the charge stored per 1 meter squared is sigma. So, unit area is sigma. So, in this area how much is stored? is going to be charge stored per unit area multiplied by the area, that is the total charge enclosed by the Gaussian surface. When you solve it, well, this area cancels off. We come to something that we have not seen before. It is EP equals sigma by epsilon. Now, this expression, the sigma for this plate is a constant. It is the surface charge density, epsilon of the medium. Now, in this equation, it does not hold a distance term r, shows that the field is independent of the distance. The field variation is independent of the distance. So, that means even whether you choose a point close to it, far from it, further from it, field intensity is the same. Now, such a field is called a uniform electric field. So, in a uniform electric field, you draw the lines parallel. If the lines are deviating like that, that shows field is decreasing, intensity is decreasing. But if the lines are parallel like that, it shows the field intensity does not vary with the distance. So, it is called a uniform electric field. You draw it by parallel lines, we used this word earlier also. And so, when we express it graphically, E vary with R, inside the conducting plate field is 0, no field. And outside it is a uniform electric field that is independent of the distance, and it is a vector. So, you have to draw it to plus and minus must be considered. Let us come to a problem. Shown in the diagram is a distribution of point electric charges. The symbols positive and negative each represent a plus q and a minus q charges respectively. So, they are equal but opposite charges, unlike charges but equal in magnitude. If several spherical Gaussian surfaces are drawn enclosing these charges, they are represented by S1 to S5, the example. Name the surface through which a maximum flux leave. So, there are two words to consider here. Maximum flux, leave. Now, let us see what we know. We have learned that from a positive charge, flux, field lines leave out. We draw the lines leaving. If it is a positive charge, lines are drawn to move out. So, we want to find flux that is leaving. So, then in that case, whatever the surfaces we consider, if the flux is to leave the surface must enclose a positive charge. Then maximum flux leave. So, in that case, we have learned the flux is proportional to field lines. We have also learned field lines are proportional to the charge. So, in that case, for this we have to find the maximum flux leaving. The surface that encloses the maximum number of positive charges must be identified. So, let us see, in the first one there are 2 plus charges, 1 minus. So, the net charge that we have to find is in the first one plus q, 2 pluses, 1 is minus. In the second one there are 2 positives, so plus 2q. In the third one there are 3 positives plus 3q, and in the fourth one there are 3 positives and 2 negatives. So, altogether the net will be plus q charge, and in the fifth one equal number of positives and negatives leaves 0 charge. So, in that case we have chosen 5 surfaces, we are given 5 surfaces. S3 surface encloses the maximum positive charge. So, that represents the maximum number of flux leaving the surface. A maximum number of flux leave the surface from the S3 surface. By competency level 6.2, we learn to express it quantitatively, and which gives the foundation to the electric field unit. So, thank you for joining with me today, and hope to see you in the next session.